Okay, good morning again, guys. It's 9 a.m. and we can continue. All right, so the last week of classes. So we're going to have another lecture on Thursday. So today we're going to finish discussing diffraction grating, and then we will start introducing ray optics. And on Thursday, again, we will spend pretty much the whole Thursday talking about array optics and okay, I just checked your chat. Okay, it looks like you figure it out. All right. Okay, and so on Thursday we will continue talking about ray optics. Okay, let me remind you where we were at the end of the previous class and what we will introduce today. In the previous class, we discussed double slit experiment. So if you create two slits, the distance between them, like let's say 0.4, 0.5 millimeters, right? And if you illuminate it with a laser light, so it must be a monochromatic source. And then so these two slits will create two spherical waves, right? Identical waves. Of course, they're going to interfere, giving us bright and dark spots behind the screen, right? And the problem with that situation that those bright and dark spots are not visible for just for us, right? Of course, you can spray something, but it's not the best solution. So the easiest approach how to see those bright and dark spots, if you position a screen. And on that screen, you can sample bright and dark spots, right? So basically, physics is not new. We just needed to adjust the formulas which we derived before for the case of a screen, right? So we introduced angles, right, to define position of a bright spot, all right? And then we discussed that measuring angles in optics, it's not the most pleasant experience, right? And so we decided to switch from measuring angles to define position of bright spot on the screen. We switched to measuring distance on the screen, along the screen, from the center of the screen to this or that bright spot, right? So, and we ended up with the formula ym equals m is an integer, lambda L divided by d, right? And the problem with that, another problem with that setup, again, so that double slit experiment, for example, can be used to measure, let's say, the wavelengths of an unknown source, of an unknown laser. But if you do that, the experimental error will be actually quite big. This is kind of, it would be a pretty bad device. Not completely awful, but not good, right? Because experimental error will be significant. And the problem is that when you see those bright and dark spots on the screen for double slit experiment, they are very crowded. They are very close to each other. Again, I usually show a demonstration during the normal semester, right? And you usually there are 10 or 12 bright spots within a couple of centimeters, right? And measuring, and they're it's not very easy to find the center of the bright spot and measure the distance between bright spot. So again, as I said, experimental error will be significant. So how can this system be improved? And that's where we finished at the end of the previous class, right? And of course, ideally, it would be good to spread those bright spots, so that instead of a couple of millimeters between them, right, you can have maybe let's say 30 millimeters. Or not millimeters, centimeters. Or maybe 50 centimeters, right? It's one way of improving the system. How can we increase the distance between bright spots? And the second, can we make them brighter, right? Okay, and we still discussed that in the previous class. So here's the formula which we derived in the previous class, which give us a spacing or distance between bright spots. And as I said, we want to increase the distance, right? So by looking at this formula, it's obvious there are two ways. You can either increase the distance to the screen, but it's a very extensive way of increasing the spacing because, yeah, usually lab space are quite limited, right? No one is going to give you large rooms, right? All right, so the most efficient way is to reduce D. And these days, modern clean room facilities in any photonic center, right? In those clean rooms, you can easily fabricate the slits, and the distance between slits can be just a few micrometers. So you see how big difference. First, we had the distance between slits like 0.5 millimeters in double slit, and now you can make slits, and the distance between them can be a few micrometers. It's a gigantic, okay, not gigantic, big difference, right? So that can allow us to increase the spacing between bright spots. Second, how can we make bright spots brighter? And again, we did not discuss this formula before. Just at some point, I stopped discussing it. Intensity of bright spots on the screen. So that intensity is proportional to number of slits or number of interfering waves. In our case, in a double slit experiment, it was two, right? So number of slits to the power of 2. So intensity is proportional to that. So, okay, if it's proportional to the number of slits, of course, okay, to the power of 2. Now, if we increase number of slits, then of course intensity of bright spots will go up significantly. For example, if you do decide to use, for example, 2 slits, then it will be 10 to the power of 2. Intensity will be increased by a factor of 100. But of course, it's even better if you, let's say, use a few thousand slits. Then, of course, intensity will be even larger. So these two natural steps, or these two improvements, allow us to make a smooth natural transition from a double slit experiment to a diffraction grating. Double slit system to a diffraction grating, right? Okay, and now, yeah, diffraction grating is used in optics a lot. Still, plenty of spectrometers based on diffraction grating. At some point, I used one, right? But of course, these days, they're kind of outdated usually, right? Most of the time now people use Fourier transform spectrometers, right? So they're faster, they are more accurate, they're easy to use, right? But still, there are still plenty of diffraction spectrometers based on diffraction grating. Okay, so let's discuss math behind diffraction grating. So I took this picture from the book. All right. So what we have, you see, we have a diffraction grating, lots of slits. Distance between them exactly the same. D, 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 and so on. You see, exactly, so equally spaced. All right. And let's justify that exactly the same formula like we used to describe position of bright spots in a double slit experiment. Exactly the same formula can be used to define position of bright spots in the case of a diffraction grating. Right. Okay, so let's assume that these lines, you see these parallel lines, purplish lines, shows a direction to the bright spot number 1, so which corresponds to m equals 1. Yeah, m equals 1. Right? And so let's show that waves produced by these slits, they interfere in this direction constructively. So let's start with the case of, for example, with these two adjacent slits. So of course, this will produce the wave, this will produce the wave. Let's show that they interfere constructively. Again, you remember that is the direction to the bright spot number 1, corresponds to m equals 1. Right? So again, so how can we convince ourselves that they interfere constructively? We just need to look at the path length difference, because the inherent phase difference is 0. So now we just need to look at the path length difference. And how can we find that difference, path length difference? You just need to draw a normal line, all right, from this slit to this direction. And you see this small red section, right? So that's the path length difference. And since this is, we assume that this is the direction to the first bright spot, so this short section, this red short section, this length equals to 1 wavelength, 1 times lambda, right? Then, so yeah, of course, if that is correct, of course, this wave and that wave interfere constructively. Then you can run exactly the same analysis for the wave produced by this slit and that slit. Again, draw a normal line, and now this small red section equals to the wavelength, lambda. Again, this wave and that wave in that direction are going to interfere constructively. Then you can run exactly the same between this slit and that slit right there. Again, those two waves interfere constructively. Again, you see any waves produced by any two adjacent slits in that direction are going to interfere constructively. But what about this wave produced by this slit and this slit, not adjacent slits? So you see, this and that. Okay, so exactly the same. Let's say what are we going to get in terms of path length difference, right? So in order to see path length difference, again, we need to draw a normal line from this point to this direction, So now what's the path length difference? It's this small red section plus the small section next to that one. And that section, again, equals to lambda because it is equal to this small red section. So lambda plus lambda, 2 lambda. So the path length difference between this wave and wave produced by this slit and wave produced by this slit, the path length difference will be 2 lambda. Again, that's conditioned for constructive interference. So wave produced by this slit and this slit in that direction, they interfere constructively. Then, okay, you can look, for example, at the wave produced by this slit and this one. In exactly the same way, you can draw a normal line. And so now the path length difference is going to be lambda plus lambda plus lambda, 3 lambda. Again, constructive interference. So now you can look, you can take any two waves, two waves produced by any two slits on the diffraction grating, right? And they all, waves are going to interfere constructively in that direction, right? So, of course, giving us a bright spot. And all those conditions is just, again, the path length difference will be all the time. D sine theta equals to integer times lambda, like we just saw. Sometimes m equals 1, sometimes m equals 2, 3, and so on. So exactly the same formula is used to describe position, to find angles, right, to the bright spots, right? So to the bright spot number 1, it's theta 1, then theta 2, and so on, right? Exactly the same formula, like what we had for a double slit system, right? Okay, and again, m, it's an integer, 0, 1, 2, and so on. All right, but again, now the same story. No one wants to deal with angles. No one wants to deal with angles, and so again, we're going to make exactly the same transition. From measuring an angle, we want to measure a distance to the bright spot from the center of the screen. So again, you see, we can introduce y-axis along the screen, right? And so now you see this is angle theta 1, which defines position of the first bright spot, or we can use y1. And then, of course, will be theta 2. You see this theta 2. Or instead of theta 2, now we can use y2. And transition exactly the same. Transition can be made using exactly the same formula like what we used in a double slit experiment. Again, right triangle, so tangent of this angle equals opposite side, which is y1, divided by the L. L is the distance to the screen. Okay, but of course, in case of a mth bright spot, tangent of this angle equals opposite divided by adjacent, or ym equals L times tangent. Right. So in exactly the same formulas. So now if I put them together, the first formula which defines position of the bright spot, and the second which allows us to make a transition from measuring angle to the to measuring a distance. So now we have these two formulas. Then, what did we do with these formulas in a double slit experiment? In a double slit experiment, this angle, so theta m and this angle, right? So theta m, they're small. They're really small, much, much smaller than, for example, 1 degrees. So in double slit experiment here, we used Taylor expansions, right? We used Taylor expansions, and we combine these two formulas to the formula which we already used, ym equals m lambda times L divided by d. But now in a diffraction grating, these angles are no longer small. And again, during the normal semesters, when I show demonstrations, everyone can see easily that in a case of a diffraction grating, so what do we have usually? Let's say here I usually show it on a wall, right? So here there is a bright spot number, the 0th bright spot, let's say in this point. Then the first bright spot, which corresponds to m equals 1, will be over here somewhere. And the grating like 2.5 meters. So the angle will be about 10 degrees, give or take. And of course, on this side, m equals 1 will be somewhere over here, like, I don't know, 50 centimeters away. So the angle will be like 10 degrees. M equals 2 will be over there somewhere. And the angle will be, let's say, 15 or 20 degrees. So now, in the case of a diffraction grating, because now bright spots are well spaced, the distances between them is quite large. So now these angles are no longer small, and we cannot use Taylor expansions. Of course, you can use if you really want that, but of course then experimental error will be significant. Will be it will be just a piece of junk. So we cannot use Taylor expansions. So it means what? It means what? We just need to use these two formulas all the time. So if you want to work with a diffraction grating, you have to use both of these formulas. Again, these give us an angle, and this formula allows us to make a transition from angle to the distance along the screen. Right? So now we cannot simplify in a double slit experiment. We did simplify these two formulas, but now we have to just use them. So be careful on the exam, right? So use the right set of formulas for the right device. Don't make those silly mistakes. Okay, so that's what we need to use. And now let's look at the that interference fringes, which can be again observed if you use a diffraction grating. Again, I took this picture from the book. So again, you see we have diffraction grating. Right. Again, it must be illuminated by a monochromatic source, something like a laser. And then as a result, we see fringes. Again, at the center of the screen, there must be all the time bright spot. You cannot have dark spot at the center of the screen, right? So, of course, this corresponds to m equals 0. Right. Then, and then, relative to the center of the screen, we have symmetrical picture. M equals 1, you see, bright spot number 1, and here m equals 1, right, and the angle theta 1. Then bright spot corresponding to m equals 2, and on this side exactly the same, m equals 2. Right? Again, you can use either angle if you're happy with angles, or you can use the distance along the screen. So again, you see now they're well spaced, then they're much brighter, and now the distance between bright spots, they're not equally spaced. So the distance between bright spots are different. For example, here you can have, let's say, 30 centimeters between these two adjacent bright spots, but here you can have 50 centimeters, then 70 centimeters, and so on. Right, so now bright spots are not equally spaced. In double slit system, yeah, all our interference fringes were equally spaced. Now it's not the story. And also, they are narrower relative to the bright spots which we had in a double slit experiment. So now this is a much better device, right? And again, as I said, it is used in spectroscopy a lot, right? Especially in old days, right? Now, as I said, yeah, less and less, because Fourier transfer FFT fast Fourier transformation spectrometers are much popular, but of course they are more expensive. All right, so now let's look at example, but I'm not going to write it. Again, before, during the normal semesters, right, I would see these bright spots, right, I would take a ruler, I would measure all these distances and calculate the wavelengths of a laser, right? So I usually use just a regular laser pointer with the wavelengths about 650 nanometers, right? Shine it on the diffraction grating. You see diffraction grating, right? And this is the wall. Usually, I use the wall, which is like 2.5 meters away from the diffraction grating, and I can see these bright spots. And actually, students even from the back seats, right, back benchers can see all these bright spots, because for the double slit experiment, students could barely see those bright spots for a double slit experiment, but for diffraction grating, everyone can see them easily. All right, so you see like Y1, again, the distance from the center to this bright spot, like 50 centimeters, again, symmetrically positioned. This bright spot, again, 50 centimeters. Then M equals 2, the distance, what is 106 centimeters, all right? And exactly distance to this one will be, all right. Bright spot number 3, 179. Again, these I measured, all right, in the lecture hall. And you see the distance between adjacent bright spots. Here, between M equals 0 and M equals 1, 50 centimeters, then 76, then what? 56, then 73, and so on. So you see, they are no longer equally spaced. Okay, so now these experimental results, as I said, can be used to measure the wavelengths, because that's what most of the time we do. That's how we most of the time use spectrometers, to measure the wavelengths or frequency of an unknown source. Okay, so again, what do we have to use? Just those two formulas. D sine theta equals m lambda, and ym equals L times tangent of the angle. And you can use any bright spot. It doesn't matter, you can use m equals 1, you can use m equals 2 or 3. Okay, I used m equals 1, right? So this bright spot to calculate the wavelengths of the laser, right? So you see, y1 is what? 50 centimeters. So you see m equals 1 and y1 equals 0.5 meters. Okay? So first, I can find angle using the second formula with this angle, right? So you see this angle, theta 1. So tangent theta 1, it will be equal y1 divided by L. y1, I measured, it's a 0.5 meters, right? You see 0.5 meters. So 0.5 divided by 2.5. 2.5, it's a distance from the grating to the screen. In my case, it was a wall in the lecture hall. So angle theta 1, okay, I used radians, is 0.197, almost 0.2 radians. Okay, so of course the next step should be, we should use this first formula, d sine angle, sine of theta 1 equals lambda, because m equals 1. But what about d? Yeah, we measured angle, so we can plug it here, m equals 1, so basically we're almost ready to calculate the wavelengths. But what about distance between two adjacent slits in a diffraction grating. You remember D, it's over here in the diffraction grating. Usually if you take any diffraction grating, which information is given on that grating? Number of slits per millimeter. In the grating which I usually use, it's 300 slits per millimeter. So the question is, how can we measure D? Okay, so here I created this sort of analysis of speculations. So again, you see what is given, 300 slits per 1 millimeter. Okay, I took a section, 1 millimeter of the slit, of the diffraction grating. And let's start with the simplest case. Let's say we have only 2 slits, right? 2 slits in 1 millimeter. Of course, the gap D, it's a gap between slits, right? D. We have 1 gap. Of course, in this case, D equals it directly equals to 1 millimeter. Okay, now let's increase number of slits. Let's say 3. 3 slits, again, in 1 millimeter. Now we have only 2 gaps, D and D. So you see, a number of gaps is less than number of slits by 1. And of course, what will be, how can we find D? We will, again, need to take 1 millimeter and divide it by number of slits minus 1, which is 2 in this case. So it will be 1 divided by 3 minus 1. So that will be a D. Okay, now let's increase number of slits. Let's say 4. Again, we have 4 slits, but only 3 gaps, D, D, and D. Again, so how can we find D? 1 millimeter divided by, in this case, 4, which is number of slits, minus 1. That's number of gaps. Right? So now you see the pattern. Now, if you have n slits per millimeter, right? You see n slits in 1 millimeter. Then, of course, how can you find D? 1 millimeter divided by n number of slits minus 1, like here, you see. 3 minus 1, 4 minus 1, but of course, in general, n minus 1. So, of course, we can apply for our case for 300 slits. So if n equals 300, of course, we can plug it here. We will get D equals 1 millimeter divided 300 minus 1. Now, of course, in real life, if you have to take a ratio 1 over 300 minus 1, who cares about this 1? It's much smaller than 300. Of course, in normal life, no one is going to take care of that 1. So everyone would just tell you, okay, forget about that 1. And everyone would just take it just a ratio 1 over 300 to get D, right? So now, okay, somebody's mic is on. Okay, just a second. No, I need to mute it. Okay. Right. So that's why every time if a number of slits per millimeter is given, people just in a lab, they would just take a reciprocal 1 over number of slits, and that's the distance between adjacent slits, right? So here immediately I just I calculated D, this D equals 1 over 300, right? And I gave you justification why it is 1 over 300, right? Okay, so now once you know D, you can plug in the first formula and you can easily measure the calculate the wavelength. Lambda, right, equals D times sine of theta 1. Again, D we just calculated, and times sine of the angle which I measured, right? So as a result, and again, it's that's what I usually do in the lecture hall. So that's basically experimental results. So what I got, 653 nanometers. The laser pointer which I used in the lecture, on the box it was written 650 nanometers. Okay, it's a quite decent result. Of course, assuming experimental error. Okay, so we're going to practice these problems in our next recitation class. For most of you, it will be tomorrow. For some of you, the day after tomorrow. So we're going to solve a couple of problems about diffraction grating and a couple of problems about double slit experiment. Okay, enough about this. All right, so this example, again, it's only worth of discussing when you show a demonstration, right? So it's a example, again, with a demonstration for a double slit. It's quite trivial, right? So we're not going to discuss it as a problem. No, it's only worth of discussing with a demonstration. You can easily understand it by yourself. We're going to skip it because we're going to look at even more complicated problems tomorrow in our recitation class. Okay, enough about wave optics. Finally, let's start discussing ray optics, a different approach of treating light. All right, I already a couple of classes ago told you the major difference between ray optics and wave optics, but let's refresh it. Right, let's refresh it. And I like this picture. All right, so yeah, this is chapter 34. These are the sections. All right, so again, how we, okay, as researchers, engineers, treat light. Yeah, God created light in somehow, some way, right? And that is our way of modeling, right? You remember that's all the whole physics. It's all about that's how we model the nature, right? So in wave optics, which we used up to this point, so wave optics is used when the wavelengths of light is comparable to the size of the object with which light interacts, right? So if you have light with the wavelengths of this size, right, and of course it's comparable to the size of the object, of course in this case, when they interact, there will be plenty of wave phenomena. So if you want to, like for example, diffraction, all right, or interference, right? Of course, in order to describe those phenomena, you must treat light as a wave. Otherwise, you would never be able to explain them, right? And again, it's a comparable. It doesn't mean that they're equal, right? Factor of 10 difference between them, it's still okay. Maybe even more, right? Comparable. And of course, in this case, you must treat light as a wave. But if, for example, like in mostly in our everyday life, right, we use visible light. What's the wavelength of the visible light? It's somewhat between 400 nanometers and 750 nanometers, give or take. So these are very, very small. Wavelengths is very small. And of course, if you want to describe interaction of that light with this flipper clicker, right? Because there's no point of treating that as wave optics. It will be ridiculously complicated, right? And a waste of time, right? It will be a ridiculous waste of time. Of course, it makes sense to treat, in this case, light differently. So if wavelength is much smaller than the size of the objects with which this light interact, then in this situation, we use what is called ray optics. So of course we treat light in a completely, in a different way, And this picture can give you an idea how we can treat light in this case. And some photograph from some church, right? And you see this light scattered on maybe some dusty air inside of the church. So we can treat light with straight lines. With the straight lines, which we can call as rays, right? Okay, so it's just a nice picture, but now let's actually introduce those rays properly. Right. Okay, so let's assume that we have this source. I know some bulb or sun, whatever, it doesn't matter, right? So let's assume that we have the source of light. And in the wave optics, so how we treated light produced by this source. Yeah, we would draw sort of wave, right? So crest, trough, and propagating this way, that way, and of course in all possible directions, right? And then, so how would we visualize this situation? We used wave fronts, right? Wave fronts, you remember, collection of crests. So you see, I connected crest crest, crest, crest. So this is the wavefront, one of the wavefronts. And then, of course, I can draw, for example, wavefront through these crests, so second and then third and so on. So we use these wavefronts to represent or to draw a wave, right? To draw a wave, right? So yeah, that's how we treated light in wave optics. So now, how can we introduce rays now? Rays are just the straight lines, perpendicular all the time. They're perpendicular to wave fronts. So you see, in this case, line, straight line, radial. And so again, at every point, for example, this point, it's perpendicular to the wavefront, perpendicular to the wavefront, perpendicular to the wavefront. And of course, direction, it's not just a straight line. It's sort of like a line with a direction, with a direction. Of course, it's not a vector. It's just a line with a direction. And of course, direction of ray is in the direction of light, in direction of light, propagation of light. So this is ray number 1. And of course, you can draw as many rays as you want. For example, you can draw this one, maybe this, right? You can draw as many rays as you want. But of course, most of the time, in order to describe this or that phenomena, I know 2, 3, okay, usually 3 rays are enough to describe something. We will see. We will look at different examples. And of course, we're going to use only a few rays. Oh, yeah, one more extra. Right. All right, for example, let's take a laser, right? So, right, laser light. Actually, it's kind of white. Okay, it's saturated probably. Let's look at the light produced by a laser. You see, laser source. All right, and this is beam, all right, a laser beam. Of course, if you use wave optics using wavefronts in this case are lines like this. One line, the second line, third line, and so on, right? So these will be wave fronts, right? We did not discuss this. In order to discuss laser light, of course, it's a different subject. Gaussian optics. Maybe at some point you will take a course about lasers. We used to have in the physics department, we used to have a nice course, lasers in applications. And now it hasn't been run for many years, right? So all this stuff was discussed in that course. But again, back to our rays. In terms of rays, all right, so you see we have a bunch of parallel lines pointing that way. Right? So that's how we can describe laser light using these rays, right? In ray optics. Okay, so now we introduce rays. So now we know how to draw them and so on. Now, what else can we see in this world of ray optics? Again, you remember we sort of went from electromagnetism into optics. Actually, optics, it's a part of electromagnetism, right? And inside of optics, there are two sections, two worlds, wave optics and now ray optics. So what else can we see in the ray optics? Of course, we can see objects with which these rays interact. All right, so which objects can we see? We usually see two types of objects. You know what, let me show you. Let's say I have this object, and you see bulb. Okay, lamp, right? So if I turn it on, okay, right. So it's one source, one type of object. And let's say here I have a smartphone, right? All right, so what's the major difference between these two objects? The major difference that this one produces light, this one doesn't produce light. So that's the major difference between these two objects, right? Okay, let me turn it off. So, and now, the first object, let's assume, for example, instead of bulb, this sun. And the second, this tree. Again, what's the major difference between them? So this object is called self-luminous because, or active source, because it produces light or emits light, as I wrote over here, right? So its major feature that it's self-luminous. It has ability to produce light, and of course that light can be described using our rays. But at the same time, the second object cannot produce its own light, right? It's passive object. So in order to see that object, we need to have an external source, active, right? So for example, this sun. So this sun produces rays, light, right, which hit this tree. These rays will get reflected, right? And then if we stand here, yeah, we can see these reflected rays, and that's how we can see this tree. And of course, if you turn the sun off, of course, we wouldn't be able to see this tree because it's not self-luminous. We need to have some rays produced by an external object. Of course, this tree can be replaced, for example, with a human being, right, with a person. But with a person, it's more complicated because, yeah, in the visible spectrum, yeah, we are kind of passive objects, right, these reflective objects. But if we, for example, move into infrared part of the electromagnetic spectrum, in the infrared spectrum, we are quite bright. You know that there are special those cameras which allows to see radiation produced, infrared radiation produced by human body, right? So so we can be we can be treated as a self-luminous object, and we can also be treated as a reflective object. It depends on the part of the spectrum, right? Right, but anyway, so two types of objects, active and passive, right? So now in this world of ray optics, we have rays, right, propagating in all possible directions, and then we have two types of objects, active and passive. Then, what else do we have to? You see, it's sort of like introducing this ray optics or any other sort of world in physics. It's like introducing a small country, right? And now we've been populating that country with members, right? Rays, now these two types of objects. So then, what else? Of course, whenever light rays propagate, of course, they usually propagate in something. It can be a vacuum, it can be air, it can be piece of glass, maybe some crystal, it can be in water, right? So every time, every time, light propagates through media. So of course the question, how can light interact with media? Let's discuss all possible interactions. So again, you see now we're introducing media into this world of ray optics. Okay, and let's discuss all possible interactions. Sorry. Okay, so and for in order to describe all possible situations, let's introduce two media, medium 1 and medium 2, in order to have a boundary interface between these two media, right? Okay, and now let's discuss all possible situations. Situation number 1, let's say a ray light, which can be represented by a ray, propagates in medium 1 and hits this boundary, this surface, interface. One of the situations, it hits the surface. Of course, conditions are different in this medium and that medium, and it's possible to have a reflection. The first process, reflection. In our everyday life, it can be compared with, for example, let's say you decided to go abroad. You go to the border, right? And I know they might not like your face, or you're something wrong with your documents, and you can be access can be denied, and you will go back to your country, right? So yeah, reflection at the border. All right. So we're going to discuss this most likely tomorrow. Wait, not tomorrow, on Thursday. Then next situation. Yeah, ray hits the boundary and manages to get into the second medium. It's called a refraction. Again, here reflection, now refraction. Again, we're going to discuss this in this course, right? Yeah, it's again, if you compare with the crossing the border, you come to the border, your face is fine, and documents is good, right? So, and you are allowed to enter a different country, right? So, refraction. But also there are two other situations. Situation number 4, scattering. Let's say this medium has some impurities. Maybe over here there's some, let's say this is the crystal, some kind of crystal, and here you have some bubbles maybe, or maybe some impurity, right? Or maybe something else, right? Some imperfection. So light can propagate, can hit that impurity or imperfection, some bubble maybe, and that light can be scattered, basically. It changes its direction of propagation. Scattering. Example from everyday life, let's say spring break, which is now officially canceled, right? Let's say you decided to go to Florida, and you go to the airport, you meet your buddies, your friends, and they will tell you, come on, you're going to Florida, it's too banal, it's too trivial, right? Let's go to some islands in Mexico, right? So your trip has been scattered, right, by your friends somewhere at the airport, and instead of going to Florida, you went to Mexico, right? Scattering. Of course, this process is significantly more complicated, right? Of course, at some point, you're going to discuss it in a higher level courses, right? For example, like scattering in just classical physics, classical mechanics, I discuss in a graduate level course of classical mechanics, right? So yeah, this is not a simple process, not a trivial. Then what's next? Absorption. Light propagates, and of course, part of that light can be absorbed by molecules, maybe atoms in the crystal, right, by some imperfections, some, yeah, there are tons of possible absorptions, right? Example from everyday life. For example, Mayflower, right? A trip from the old world to the new world in when was it, like 17th century, beginning of 17th century. Okay, so at the very beginning of the trip, let's say 200 people were on that ship, Mayflower, right? And then after sailing for, let's say, 2 months in the ocean, right? Not everyone managed to get to Plymouth, right? Some of them actually died, right? And they were absorbed by the ocean, right? So, absorption, right? So, again, this process is not very simple, and okay, I will tell about the review session, right? So, some people were absorbed, and the same with light, right? Some amount of light can be absorbed, and of course, intensity of the light at the end will be smaller than intensity of the light at the very beginning, right? Again, this process can be, will be described in a higher level course, because again, it's not completely trivial. So we are going to discuss reflection and refraction, right? Okay, so now we introduced rays, we introduced object, active and passive, and we introduce media and interactions of rays with media. So basically now we have everything that we need in this world of ray optics. And now let's start with the simplest process, reflection, and then next class, refraction.